ये लाइट पोस्टर है बस बाहर वाला पोस्टर है बाहर वाला पोस्टर है
नहीं currently actually ascending phase of the. There is a bit of echo, so maybe.
Yeah, yeah.
CABs. So it is important to understand why they are, first of all, exploding. If they explode, then what will be their path as they travel into the interplanetary medium? So we need to understand their velocities, their direction, and then only we can get a knowledge about the arrival time in the sun, in the Earth, because we have to understand their impact as it reaches close to the Earth, which affects our neighborhood. This is again another movie showing that if an ejector comes out all the way from solar disk, this is the image of the sun in the lower corona. We call these middle corona and the outer corona. These are all different instruments. Why I'm showing this is that it is still not possible to do this again comprehensive thing by one single telescope or one single instrument. This is an image from taken from stereo spacecraft. And by combining this information of an imager and two coronagraph, and these are called heliospheric imager, we are now able to track these CABs all the way from the sun and as it comes near Earth. So it is important, although we have Aditya mission, it is important to still work very closely with other international missions from ground and space to get a comprehensive understanding. So thankfully, we have our magnetic field. Earth has its magnetic field. So this huge ejector, when it comes, we are protected. But of course, this protection is up to a certain extent. When these charged particles comes, they cannot penetrate. So these huge magnetic cloud, what you see here, they carry very highly energetic charged particles. Thankfully, because of the Earth's magnetic field, it shields us. But what will happen is when this charged particle comes here, they can, move around these, magnetic field lines and can try to enter through the poles, because there is a, you'll see from the next movie. Normally, if you have if it is considered that the Earth has only this kind of a dipole, and this would have been the magnetic structures here. But because of the presence of solar wind, this is another thing which comes as a continuous expansion of the outer atmosphere of the sun. This behavior of a simple dipolar magnetic structure gets completely, changed. And this is what is normally Earth's magnetosphere looks like. But again, when there is additional to the solar wind, when these CMEs do arrive, then they disturb these magnetic field lines, and charged particles will try to enter through the polar regions. We'll see what is the effect of that. But occasionally, it can also disrupt these magnetic field lines completely, depending on the orientation of the magnetic field line direction and the CME, or the cloud which is coming, their magnetic field orientation. You will have geomagnetic storm. So that's the effect. So the solar storm is causing a geomagnetic storm in our magnetospheric environment. So this has a much more severe implications. Of course, you have seen beautiful auroras. So as I indicated, the particles spiral down the magnetic field lines and collide with the atmosphere to produce the aurora. So these beautiful auroras are seen because of direct interaction of the particles with the Earth's atmospheric layers. Now, what I indicated, what are the effects of the geomagnetic storms? It disrupts our radio communication. It impacts our electrical power systems. You can have a complete blackdown. And these blackouts it did happen, and particularly in northern hemisphere or higher latitudes, these are very severe. In fact, in Canada, it happened several decades back, and then there were several hours of blackouts in cold conditions. The metro stopped and all that, and the insurance companies have to pay a few $1 billion. So this is a very serious thing now in terms of our humanity, because we are so much dependent on our communication system, our power systems. This is again example showing the GPS, and the GPS will take you to the wrong direction, and if you do the Google map. And then, of course, you are watching the India-Pakistan match. It can be also disrupted because your TV, can be, discontinued as well. So it does impact our day-to-day life. This is a summary of how it impacts. These are the huge solar flares, which generates the solar coronal mass ejection, and they carry, the highly charged particles. They are cosmic rays, and as I indicated, the solar wind, it impacts the ionosphere. And ionosphere is actually heavily, filled with our communication system. It directly affects the satellites. Of course, if you are planning for a spacewalk, if you are rich, you can take journey to space, of course, you will be directly affected. So we can get good money from your Mars. They say that, please give us some $1 billion to ensure that your space walk will be safe. So this is an important thing. There's also something, it's written here as atmospheric drag. Incidentally, the same person who launched 40 satellite with the SpaceX, they lost all the satellites just a little more than a year back, because they were not aware that even a middle class solar storm can disrupt the environment in a way the solar wind drag was changed. So when we launch a satellite, you see it moves into a interplanetary medium where there are certain magnetic fields and certain motions. So if you do not have a complete understanding of the medium through which you have to travel, your trajectory can be changed. And that's what happened in the case of the SpaceX. And then they lost 40 satellites. So again, you can imagine how many dollars were lost in that. So it disturbs our radio communication. It also affects our electric grid. As I indicated about this blackout, telecommunication gets disrupted because of the induced currents in this. Now let me get into Aditya. We were thinking about Aditya for more than a solar cycle. This is what is shown is again the sunspot number. These are minima, and then you have maxima, and then again minima. So we started actually way back in 2006 for a low Earth orbit mission. And initially, it was only a imaging coronagraph at low Earth orbit, which was approved in 2009. We started, designing it, some manufacturing and all that happened. But then something happened. Professor U.R. Rao, who was the ADCOS chairman at that point of time, of course, former ISRO chairman as well, again, another visionary. He just, called a few scientists and then said, would you like to go to Lagrangian 1 point? We couldn't believe. Actually, to be honest, I was much younger. I have experience with SOHO because I worked with the SOHO from, after my PhD. I couldn't believe actually, it is real what I'm hearing that we could reach L1, because that's a long journey. And it's only European Space Agency and NASA has achieved that yet. So with his blessings and motivation, we did get expanded Lagrangian 1. And once it was Lagrangian 1, of course, announcement of opportunity was there. Several institutes submitted a lot of proposals with new instruments, and a small satellite program with one payload, that too with the imaging capability alone, was expanded to a full-fledged observatory class mission. So that's a big step forward. Of course, we took a while. With the minimum, we also had the COVID challenge. So it took a while to get all the instruments ready. Finally, the payloads were delivered earlier half of this year. And with the fantastic skills sense of ISRO and the team, the launch was possible a few days back. So this is quite amazing. We are, as you can see, we are in the ascending phase of the solar cycle. Solar maxima is near. Probably next year, we may have a lot more activity on the sun. So this is a really, really ideal time to launch. And we expect them to be there for at least one solar cycle. Of course, the nominal period of the mission is 5 years. But normally, if you reach Lagrangian 1, you can live longer. That's expectation. Now, that's the trajectory which we all experienced from Sriharikota the other day. The liftoff took place, and the separation happened about an hour later. And this was, of course, lifetime experience for me. So now we are actually in this. The laser pointer is probably not. Okay, let me. This is good. Yeah, you are in the planetarium. Of course, you have good laser. So this is the Earth orbit which we are now taking. And you can see one by one, we will go to a larger and larger orbit. And eventually on 18th September, which is incidentally my birthday, we expect to slingshot and then go into the cruise phase. Of course, this is a long journey, and this cruise phase will be almost 4 months. This is a very critical maneuver to get into the Lagrangian 1 orbit. This is actually quite a complicated thing. It's not a real one single planar motion. So that's why a lot of confusion is there. What exactly is Lagrangian one? I will explain a little bit, and I can discuss with you later on also if you have more questions. So basically, there are 5 Lagrangian points for a two-body system. Suppose you have one as Earth and one as Sun, and if you put a third particle, in this case a satellite, so around this Lagrangian one point, this satellite will make a orbit, not in one plane. Please be aware that this is a 3D movement, 3D space movement. It's very quite complicated. It's not going to stay in one particular halo orbit around. So that's why the terminology is called halo. Essentially, it's almost like a Lysage's figure if you have seen this. And basically what happens is the satellite, to stay in any circular or any orbit, it needs a centripetal force. And that centripetal force is somehow balanced or supplied by the pull between the sun and the satellite and the earth and the satellite. So that balances. So all the time in the time evolution, that has to be balanced. And in that process, once you reach Lagrangian one point, you can stay much longer. Normally for any satellite trajectory, you continuously need to have the thrusters to sort of push it. So a lot of fuel is used. But here in this particular Lagrangian one orbit, once you are there, you need only marginal corrections, probably once in a month kind of time scale. So that's the reason once you reach Lagrangian one around that area, you are expected to live much longer with the fuel which is remaining with you. In fact, the SOHO is still alive. It was launched in '95. Of course, majority of the payloads are not, operating with its efficiency, but the satellite is still alive. So that way, if our instruments do survive, we expect them to be there for much longer and at least steady one solar cycle. Now at Lagrangian, as I indicated, it is only NASA and ESA missions at this point of time for solar observations. This is the SOHO and the WIND and ACE. These two, 3 satellites are there. I must point out these two are mostly for solar wind studies. SOHO was again a suite of 13 instruments, a combination of remote sensing and in situ. This is exactly what we have with Aditya-L1. Of course, the L2 you have heard more recently because of the James Webb, and the James Webb and Earth actually protects this a little bit from the sunshine. So because James Webb is doing infrared astronomy more, it helps in that process as well. Of course, there are other 2 Lagrangian one point is L5 and L4. This is really ideal for solar observation, because what happens is when we are sun-earth line, then we are able to see this side of the sun. Sun. We don't know what is happening behind. Of course, if L3, the sun-earth line is here. So and then L3 is behind the sun, which could have been ideal, but if you go to L3, there won't be any telemetry, so we can't get any data. So L4, this is L5 and this is L4, looks at from the side. So the evolution of the sun in number of say almost a week in advance, we can see if some active region is coming and so on. So that way it is a very good vantage point as well. And maybe in near future we may go there as well. So I must also point out that, as I indicated, that these kind of missions do need support from the international community. ESA is providing us some ground support. In fact, after the launch, the satellite was actually being able to again track from Fiji Island. So we have some downlink available through the European Space Agency, and so during the initial phase of 6 months, we are taking help from European Space Agency, particularly for their ground network, deep space network. Of course, the L2 James Webb, as I indicated, and this our cute L1 Aditya fellow is traveling to there, and we hope we'll be there. So this is animation done by our students, again explaining what we are expected to do around L1. It's not that we are going to sit in L1, but we are basically going to go around L1, look at the sun continuously. That's again a very important area, because if you would have been a low Earth orbit, there would have been, disruption and eclipses, which will not have given us continuous viewing of the sun. Science objectives, of course, what I intend is we'll go rather quickly these slides, and I will expect that we have several posters outside, and my team colleagues, my fellow faculties, they are more knowledgeable. So you should interact with them to understand a little more about each topic. First item is coronal heating. So corona is much hotter than the lower atmosphere, namely the photosphere and chromosphere. This has been a mystery. We do understand, certain details about why corona is so hot, about millions Kelvin, but we still do not have a complete understanding. So we expect that our payloads will shed more light into the comprehensive understanding. Solar wind acceleration. As I said, that outer atmosphere of the sun is continuously throwing away particles. Initially, it is only 10, 20, 30 kilometers per second. But as we go away from the sun, the solar wind is few hundred kilometers in the equatorial region and 700 kilometers in the polar regions and so on. So there is a very big asymmetry in the solar wind, behavior. Why and how this, solar wind gets accelerated? What is the physical process which is responsible for the solar wind acceleration? That's one of our major scientific objectives. Solar atmosphere is actually, the different layers are very much coupled. Very similar to Earth's atmosphere, you have stratosphere, troposphere, and then mutually ionosphere and so on. They are actually talking to each other. They're not isolated. So to understand the coupling, you need again multi-wavelength observation, because they probe different plasma layers of the atmosphere. And at Aditya, we have again a multi-wavelength capability, which allows us to look at different layers from the full disk imager as well, which is called the Solar Ultraviolet Imaging Telescope. Then we have solar wind distribution and temperature anisotropy. This we will be achieving through the in situ instruments at Lagrangian one point. And as I indicated, why this coronal mass ejections are initiated. What are the different processes which drives flares? These things has to be understood close to the sun, and then their impact near Earth space weather can be only studied when we have a combination of in situ and remote sensing together. So that's a thing. There are several uniqueness. I mean, often people ask, there are so many, already space-based platform. Why are we going again? So there has to be some uniqueness of your instruments. So what we did, the solar community, primarily, we have been discussing with each other for decades and try to identify the gap areas, that what capabilities other space observatories do not have. So we are going to first time spatially resolve the solar disk in the near UV band. There were small balloon experiments which demonstrated how this near UV 200 to 400 nanometer is very important. Then CME dynamics close to the solar disk, because we have a coronagraph which is going to look very close to the sun, thereby providing information on the acceleration regime of the CME, which is not observed consistently. There have been some ground-based observatories which has attempted that, but there are lots of challenges of coronagraphs having the ground, and of course, discontinuity in terms of the time of the day and so on. So it is important to have CME's observations close to the sun. Onboard intelligence we have implemented, because one thing is there that we are going farther away. That means your data link becomes slower and slower. If you have a near Earth orbit or if a geosynchronous orbit, you have a much better telemetry. That means whatever data you collect, you can quickly transfer it to the ground. Once we go farther away, that limitations are, the total data volume can be much more restricted. So what we have to do is, see, we are taking continuously images of the sun, but we are going to discard some of them which are not so useful. So we have automatic intelligence. For example, these days CCTV cameras are there everywhere. But when CCTV cameras is recording, sometimes they only detect motion. They're called motion sensor cameras. That means if you see any motion within that frame, a subsequent frame, you only save those images. You don't save, in the middle of the night, probably you don't have any visitor. You have a camera in the security gate. So you only capture when there is somebody moving into your frame. So this is a similar thing, because CMEs are transients, right? So they are only coming once in a while. So when they are coming, we need to capture them because we are not able to continuously monitor the CMEs. So that's the idea of having onboard intelligence. So we have implemented that. And then, of course, as I indicated, the solar wind direction and is very important. The energy is not distributed, uniformly in 360 degrees. Rather, it has lots of complexities and polar variations and so on. That one also we need to capture. So these are the payloads. We have four, remote sensing instruments. The biggest guy is called the Visible Emission Line Coronagraph. Again, I will say little things about this, but more will be available outside or in the questionnaire session. We have the Solar Ultraviolet Imaging Telescope, which are going to look at the full disk images. Then we have, these are the particle. We have two X-ray spectrometers, one called SOLEX, which are going to look at the low energy, and Helios is going to look at the high energy, X-ray flares. Now, what we understand is in Sun there are very small guys, there are medium guys, intermediate, slightly bigger, and the big fellows. And all these, different classes of flares are providing a lot of energy, and probably they are actually be able to give the sufficient energy to heat the corona. So that's one of the ways of explaining the coronal heating. But we need to capture all different classes of flares. So far we were not able to capture all the flares. We were mostly focusing on the big ones. The small ones, they are numerous, but they are very difficult to detect. So that's the focus of the SOLEX instrument, low energy spectrometer, and the Helios will capture the big ones. And of course, there is a magnetometer. Basically, this is a boom, and we have probes on this boom, which will detect the magnetic field of the interplanetary, L1 position. And also, if a big magnetic cloud travels from the sun and reaches Earth, then it will, capture the magnetic field of that magnetic cloud. There is a poster outside here which describes all these different payloads, its functionality and all that. I will again ask you to go around and interact with my team so that you get a better understanding or full understanding. Again, these are the details of these individual payloads, where they're located, where they were built. This is again multi-institutional. Primarily, the main payload, I must point out, is the coronagraph. There's a big elephant sitting in the top deck. This is built at Bangalore, Indian Institute of Astrophysics laboratory in Hosakote, and the suit was built in Pune, Ayuka. Then it came to Bangalore, and the URL center, clean room facility was used for integration of suit. So these are the two, I would say, big fat payloads. Others are much more smaller and tiny, but they have importance in terms of the comprehensive science. So this is the two X-ray spectrometers which I was referring to, which was built in. One was in Physical Research Laboratory, which is again another center for ISRO, and URL Center has built this SOLEX instrument. I must point out that all these is for the next generation. So it is important to have training. And at Nainital, we have initiated this support cell. If some of you are aware, AstroSat mission also had a support cell at Ayuka. Thankfully, ISRO has given us this responsibility to reach out to younger people who are interested to work on the science data. So we are conducting regular training workshops, and these workshops are going to be all over the country. We have our 5th workshop in IIT Kanpur. Already 2 10-day workshops was there at ARIES Nainital last year and this year. We will continue that more vigorously coming years, months and years, to train people how to work with us Aditya data, what are the different instrument capabilities, and then how you can submit proposal. You see, these are observatories. Observatory means the instruments have a lot of complexities. So you need to understand the instrument first to be able to use the instrument for scientific proposal submissions and all that. So these are proposal submission system, which again ISRO has developed at ISSDC. We will be understanding how this proposal submission system works and so on. So exciting time. We were there inside. As you can see, it's a lifetime experience. We have been attached with this mission for more than a decade now. I was, fortunate to be part of it. This is the project director, Nigar, has been working, I think, more than 10 years now, day and night. This is again such a huge change of working style. I mean, we are all part of different government organization. We don't sleep, and they don't sleep either. You can imagine how it is that with the Chandrayaan landing within even few weeks, they have launched this PSLV stuff to go to Lagrangian one. So these are challenging missions. These are not small, regular, day-to-day affair of ISRO. ISRO is interested to take more challenging tasks. And again, the visionary of Professor U.R. Rao and subsequent chairman and so on, and with the government support now what we have, I think we are able to achieve this. So that's the satellite before it was launched. This is the team I have today. Dr. Pant and Dr. Prasad is now already outside setting up the poster areas and so on. And some of my students have already flew to US. He's involved in that. He was actually the person who designed this, onboard intelligence. Now he's doing it for a NASA mission at the US. So please feel free to interact with them. And thank you for your attention. I come from a beautiful location at Nainital. Basically, this is taken from our new observatory site at Devasal, which hosts, incidentally, the largest 4-meter class 2 optical telescope from this part of the globe. Since you are in Delhi, please feel free to visit us. So that's by email address. You can write to director as well, and we'll be happy to host you. Thank you for your attention. And I will really be happy to interact with you as much as possible. Yes, please feel free to ask questions. We have plenty of time for the rest of the day. Maybe we can have a little more light. So when you ask the question, I will try to come closer to you because we have only one microphone. Otherwise, I will repeat the question also. So somebody has to be the first. Okay, so there is the young boy in the back. You shout, I will repeat the question. The magnets in what? Yeah. So, during the aurora, of course, as I indicated, the auroras are basically visual things which is happening